as well. Okay, so a slope field. A slope field, also called a vector field, also called a direction field, like I already said, is going to give us a visual of a differential equation. It's going to show us what the curves look like that are the solutions of the differential equation. And it's going to show these curves by the nature of sketching little lines that represent the curve of the slope of the curve. As we represent the slope of the curve, you'll be able to see that the overall pattern will sort of give you an idea of the look of the curve. All right, so let's take a look at a really simple differential equation, and we'll make a really simple slope field to kind of get the idea. And that's the differential equation that says dy over dx is equal to x. Okay? dy over dx is equal to x. So if dy over dx is equal to x, then if we wanted to kind of think about values for dy dx, the values of dy dx would just be equal to whatever x value I started to think about. So, for example, if x is 0, the value of dy dx would be 0. Now, how we're going to represent that graphically is we're going to go to, on a coordinate plane, every point. Okay, so all the points where x is 0, and we're going to show a little line that has a slope of 0. Because that's what this particular differential equation says, is that dy dx equals x. So when x is 0, dy dx, or the slope of any tangent line, would also be 0. All right, so if I'm where x equals 0, I'm on the y-axis. So all of the points that were highlighted here, those are all points where x equals 0. And so at each of those points, I'm just going to sketch a little line to represent a slope of 0. And we've taken our first step in creating a slope field. Now, if we go to the next axis, all the places where x is 1, I'll draw a line with a slope of 1. We're just going to eyeball a slope of 1. Nobody's ever going to come to our slope field and measure our little lines and be like, nope, that doesn't have a slope of 1. It has a slope of 0.9. They're never going to look at it and go, well, that's a slope of 1, but that's not really a slope of 2. That's a slope of more like 1.8. We just want to make sure that these make sense as we look at them next to each other. So if I do a slope of 1, right, so that part was my slope of 0. This part was my slope of 1. A slope of 1 kind of is like at a 45-ish degree angle. Okay, it sort of cuts, then having the grid there kind of helps, and you can kind of eyeball that. So if I'm going to draw a slope of 2 everywhere x is 2, those are just going to have to be steeper, closer to straight up and down than slope of 1. Slope 0, completely horizontal. Slope 1, kind of like a 45-degree angle. Slope 2, a little bit steeper. And then if we had to do slope 3, 4, 5, 6, we would try to progressively just get steeper and steeper and steeper and steeper. Like I said, nobody is looking at these and measuring them with any kind of precision. This is a sketch. So it's just kind of like the overall feeling like, okay, oh, about slope of about 1. So comparatively, what would a slope of 2 look like? Now, if we go on the other side, and remember this differential equation was a very easy differential equation, so it's very easy to come up with the slopes. In other problems, we might have to think a little bit more about what the slopes would be like, because they might be combinations of x's and y's. In this problem, the slopes are just the same as the x's. So the other half of this slope field would have some -1 slopes when x is -1, and then some -2 slopes when x is -2. So that's my -2 slopes, my -1 slopes, my 0 slopes, my 1 slopes, and my 2 slopes. It's kind of like a contour map, like you may have seen with that you know. All right. So far, so good? Yeah, it's just a bunch of little lines. Now, if they say, dy dx is the same as the slope of the y equals f of x function. Okay. If they tell us to sketch a specific solution or a particular solution, in this case, it says a particular solution through 0, -1. I am going to go to the point 0, -1, right there. Now remember that that was a straight, flat slope. And I'm going to draw a curve that kind of follows the path of the lines. So if I kind of follow the path the lines are pointing, the curve I'd be looking at would look something like this. Looks a lot like what function? Y equals, like a y equals x squared. Yeah, it looks a lot like a parabola. Okay. And if they had told us different condition points, we may have, I'm going to move this, we may have put this parabola in different places, but, you know, wherever you anchored it, there would be kind of a path of lines to follow. So this is a picture of almost like a lot of parabolas. And it's sort of suggesting that the solution to this differential equation, the solution set of equations, are all parabola equations. Now, what if I take this and I said, let's do separation of variables. dy over dx equals x. That would mean that dy equals x dx. Not much to separate there, just cross multiply. If you think about that as like x over 1. And this one's kind of really boring because you're integrating just dy, and that's y. And you're integrating x, which is x squared over 2 plus c. So what I got solving and what I got through sketching my slope field kind of match. My slope field sketch says, hey, I think this differential equation is the differential equation that represents a group of parabolas, which happen to be written as x squareds. And when I do the solution for this particular, since this one can be separated and integrated, a little bit of separation of variables, heck yeah, this differential equation is the differential equation that goes along with a group of parabolas. Y equals x squared over 2 plus c. On a much more sophisticated level, this is something that scientists can do. They can obviously have computer programs that would do this, so they can put in a more complicated differential equation and get a model, sort of create a computer-generated model that starts to suggest what the solution curves look like. All right, any questions on this first problem? All right, so why don't you, I don't know what's happening here.
Sorry, I don't want to interrupt. I was just wondering if I could see my test, because I saw the grade in the grade book and I'm confused on how I got that.
Yeah, we're not gonna do that right now, okay? But I can email you later and we'll talk. Okay, all right. All right, friends, so let's look at the second one. And let's try a little bit, see if you can come up with my values and my sketching, please. See if you can come up with what the values are going to be. In this case, dy over dx is 1 over x. Find some values for the slopes that you'll need to draw on the slope field. And see if you can draw some sketches of some slopes. And if you just want to draw in like one that goes with each value instead of drawing like the whole group because you're not 100% sure and you don't want to have to erase a bunch, that's fine. Just draw a couple. So this is 1, 5, 1. All right, so let's take a look at this one. Let's zoom this down a little bit. Once again, it's really easy to sketch when you have a pretty simple differential equation. In this case, the slopes are just equal to 1 over x. I always do the easiest ones first, and the easiest ones are either the zeros, which are horizontal, or undefined. And to draw slopes that are undefined, I'm going to draw a vertical line. So I'm going to have these little vertical segments right where x equals 0 in this case. And then another set of x equals 1. So this is undefined. This is 1. But then the next group is a half. So a half slope is flatter than a 1 slope. It's less up and straight up and down. It's more towards the horizontal. So, like I said, it's just really as compared to what I did for 1, when I do my 1/2 slope, they should look a little flatter. Positive half, so they're from left to right, uphill, so they're still uphill little lines. but the lower that positive number goes, the lower that number goes from 1 to 0, the flatter the line is. And then we kind of have the opposite kind of behavior with the negative 1 and then the negative 1/2. This case, I'm going to go 1, 0. A vertical line set of slopes sort of acts like an asymptote. So when I start sketching a picture, the curve, I can't cross over that wall of vertical lines. And I'm going to trace over that again so I can move stuff around. All right. Now this one's a little different because you might say, well, this side looks one way, right? But if we were over here, actually, I don't think I can flip it over. I can rotate it, but I can't flip it. This side, it's kind of like this side, but it flipped over. So if we were drawing something over here, it would look a little bit more like that. So the group of equations, there's a little bit more difference in sort of like two groups, whereas all my parabolas would have kind of been the same, but with the top one over here, there's some that would be over here, some that would be over here. Anybody recognize this function? It's got the vertical asymptote, kind of curves like that. That's a natural log, yes. This is a natural log function. Okay. And let's check this one out. dy over dx equals 1 over x. If we did a separation of variables, I would get x times dy equals dx. That's me cross multiplying. So dy equals dx over x. And so if I separate and I integrate in this case, this is for sure a natural log. This differential equation matches up with a set of functions that are natural log. Where did I put it? Let's see. Put it somewhere safe. Under all this? I left it laying here. It's here on my desk. There it is. There's your lab.
Oh, there's my lab.
There's Eric's lab, and then that. There's that. There it is.
Thank you, sir.
Okay, you're welcome. Okay. Now, questions on number 2. When you do a slope field, all slope fields are not going to be something you can separate. Oftentimes you're asked to do a slope field for something that you can't separate. And it's not really something that has a nice looking picture to it. So it's going to be hard to kind of get a good idea. You know, we're not going to be able to look at it and go, oh, this is secretly natural logs or something. It's going to look like a lot of crazy stuff. So on something like this, on problem number 3, if it says, hey, if dy over dx equals x plus y, draw a slope field, let's go ahead and just kind of limit our points a little bit. Let's go through where x goes from -2 to 1, and let's let y go -1 to 1. So we've got this whole grid here, but we'll say we'll just kind of focus on that one little section, those 12 points, sketching what would happen with the slope field through those 12 points. Okay. So one way to do that is to kind of create a table to help yourself organize your work. Okay. So if we think about our x's going across, we have an x of -2, we have an x of -1, and we have an x of 0, and we have an x of 1. We have a y of 1 and 0 and -1. And so in each little box, I'm going to write the slope. If I draw a little box right here, the result of x plus y. Okay. This is just one way to organize it. You don't ever have to do this. The people who, when they grade your slope field, they're going to look at probably a couple points specifically and then kind of just grade it holistically. They'll look at it and go, yeah, that one looks good, that one looks good, everything looks good in relationship to it. Great. +1 or +2 if it's worth 2 points. They're not going to go back and look at these calculated values. But this is a technique that lets you calculate the values with some kind of organization. Because then if I say, okay, that's -2 plus 1 is -1. -1 plus 1 is 0. 0 plus 1 is 1. 1 plus 1 is 2. I could actually erase this for a minute. That box, let me do a little highlighter. It's going to kind of highlight the section we're doing. I could take that whole set of slopes and put those on my graph. If I organize it like this, then I can go to the point -2, 1. And there's my -1 slope. There's my 0 slope right next to it at -1, 1. And there's my 1, and then there's my 2. I find it easy to go across and kind of do a series going across. You can also do a series going down. It's harder when all the way across or all the way down is not the exact same slope like we had on the first two. Because this row is going to be -2, -1, 0, 1. And it's like at 0, 0, my slope is 0. I like to do the zeros first because they're easy. And then I have a +1 slope, I have a -1 slope, and then a -2 slope. And then this is -3, -2, -1, 0. So we definitely have a pattern of behavior. and how this is going to get graded. Number one, they look for the zero slopes because those are easy to find. Those are easy to check. Are all the zero slopes in the right places? Check. Is everything else kind of makes sense in relation to that? Positives versus negatives, getting steeper, in this case, as you go away from the zeros. It doesn't look like anything specific. It's not like we have something good to follow. Something like this, often they don't even ask you to sketch a picture because it's kind of all over the place. Because check out this differential equation. It's not separable. That means it's kind of a weird relationship. That means it's kind of a weird function that created, if even a function, that created this particular differential equation. I think doing 9 to 12 points for the practice problems that we're doing makes a lot of sense. Like I said, on the AP exam, if they ask you to draw a slope field, they will say, okay, here's the grid. They'll give you the grid in your book, and they'll pick certain points. And they'll say, at the points where there's the dot, draw the slope field segments at those points. Because then they know exactly which ones they're looking for, and probably they're going to have some that are zeros, so they can check those easily, and then positives versus negatives, and so on. So these two are here for you to do to practice. Like I said, I think a little group of 12, I mean, Mr. Walters he just didn't edit it. He did a -5 to 5, 25. If you want to do 25 points, you can. I think this little group of 12 is probably enough. Let's take a real quick check at a matching question and talk about the strategy on that, and then we should be in good shape for today. So, in multiple choice, one option might be, here's the differential equation for slope field choices, which slope field matches the equation? Or vice versa. One slope field, 4 equations, which equation matches the slope field? Now, you can imagine me, not visual, number one, and never learned this myself in any calculus class. The first time I saw these problems, I thought, oh crap, how am I going to do that? Because I suck at stuff like this. So, like a lot of things that I'm not great at, I figured out sort of like, well, how am I going to make it easier for me? Because some of you are going to be good at this and some of you are going to be more like me, like, I suck. So usually what I do when I start looking at slope fields and try to do this matching, a couple things I start looking for are where the slopes are equal to 0. Either from an equation standpoint or from a graph standpoint. It kind of just depends on what we're faced with the problem. So, like if I look at graph E, I see all these horizontals there along the y-axis. So E would have to match up with a slope field, with a differential equation that would tell me that every time my x is 0, my slope would be 0. Every time my x is 0, the overall slope would be 0. That wouldn't happen in A, because when x would be 0 on A, the slope would be 1. that wouldn't necessarily happen on B. B would have a 0 slope if x and y were the same. But when x is 0, unless y was also 0, we wouldn't have a 0 slope. C doesn't even have any x's in it. But D, if I put a 0 in for that x in the numerator, 0 over any y is going to match up with 0. So choice D and slope field E must go together. Anything else you can match up? How about letter G? It's hard to see this on letter G, but I'm pretty sure on the graph of letter G, all the 0 slopes are along the x-axis. So those are all 0 slopes when y equals 0. So I'm pretty sure C matches up with G. Which one does A match up with? A matches up with H. How do you know that? It's okay. Let's put it in the basket, Josh. Say that again.
F matches with B, so then the only one that's left is A.
Okay, so F matches with B. All right. So why does F match with B? I agree. And A matches with H. How do we know F and B match? Where are my 0 slopes on F? When x and y are equal, right? When y equals x, the slope is 0. So right along that y equals x line, we get that slope of 0. In this case, we get a slope of 0 everywhere that x equals -2. Because if you took this equation and plugged in x is -2, 1/2 of -2 is -1, plus 1 would make 0. So for me, 0 slopes helps. The 4 you're going to try to match up in example 7 are a little bit trickier. Okay. But 0 slopes is definitely one of the things that you can look for. All right. That is